Academy. Today we're looking at chapter 12, physics, and the topic is light. Okay, let there be light. So let's quickly take a look at light. Light is a natural phenomenon. It's the fastest phenomenon created by Almighty God that we know of as of today. It's the fastest thing on earth. Nothing travels faster than light. The speed of light is about 3 times 10 to the power of 8 meter per second. Okay, to the power of 8, that's 300 million meter per second. This is the speed at which light moves in a second, in a blink. In one blink, this is the speed at which light travels. So it's very fast. Light is very fast. It's the fastest thing on earth. Okay, it can act as a particle and same as energy. It can act as matter as energy. When you study in grade 12 or A level, you study particle duality, light particle duality. Okay, so light travels in a straight line, in form of ray, travels in a straight line like this. Okay, single one like this is called ray, R-A-Y, ray. A single one is ray. Okay, multiple ones are called beam. Okay, they are called beam. Multiple ones are called the beam. If you have them many like this, many rays together are called beam of light. Okay, so one single one is called a ray of light. So light travels in a straight line. We have to keep that in mind. Light travels in what? A straight line. Now let's take a look at, before we delve into light proper, let's take a look at some of the colors. Okay, because light travels in different colors, comes in different colors. Now, I say, how do your eyes see the colorful musical fountain? Assume this is a colorful musical fountain. How do our eyes process them? We see them in shades of different colors, right? Now, how do the color get into the water? By reflection, right? By reflection. They reflected into the water. And how does the light and water interact? How do they interact? When they touch each other, they reflect, okay? Because light is able to reflect. Now, let's take a look. As a result of that, let's talk a little bit about reflection. Light can be reflected off surfaces, off objects. If light hits a surface, it can be reflected. The kind of reflection depends on the surface. If you have a smooth surface, you have a smooth reflection. Like, for example, if you have a plane mirror is a smooth surface, okay? When light hits a plane mirror, it's going to be reflected, rebound, okay, to be rebounded. Okay, let's say, for example, this is normal. You have a normal line. Okay, 90 degrees to the mirror. Okay, normal line is always 90 degrees to the mirror. Now, the ray of light that is coming to the mirror is called incident ray. It's called incident ray. Okay, when it hits the surface of the mirror, this is incident. And the angle of incident is the angle between the normal and the incident ray. This is the angle I, the incident angle. This is normal. This is normal. This is the normal line. And then when it hits this is the boundary, this is the mirror, okay? When it hits here, it will be reflected with the same equivalent angle this way, to be reflected this way, with the same equivalent angle. So you show that it's moving away, it's reflected. So you use the arrow to show it's being reflected. So this is angle arrow, this angle arrow. This arrow and angle I, they're equal, okay? They're equal. So this is one characteristic of light. It's being, when it hits a surface, depending on the surface, depending on if it's a smooth surface, then to be regular reflection. To be regular reflection means the light can be reflected equally. The same angle of incident and angle of reflection will be equal. Okay? And if it's a rough surface, it will be reflected unequally. Okay? Let's say this is a surface that is rough. Okay? A rough surface, not a smooth surface. When light hits here, instead of being reflected equally, no, it may be reflected like this. It may be reflected like this. You can see if you draw the normal line, you see the angle of incidence is not equal to the angle of reflection in this case. You can see the angle of incidence is not equal to the angle of reflection. This is rough reflection. Okay, so light reflected off objects, in this case, is musical fountains. It goes into our eyes, right? Our eyes receive the light in the light sensitive cells called the retina. So light that travels to our eyes is being received and processed in the retina. We're going to talk later. We'll talk about the defects when you have long sight or short sight. When you have long sight, the image will be formed after the retina. When you have short sight, the image will be formed before the retina. What kind of lens do you need to wear to correct the long side effect and the short side effect. So now let's take a look at the first segment of this section. These are the things we're going to learn. Reflection of light. In this reflection of light, we're going to look at define the terms normal, angle of incidence, like I've mentioned, angle of reflection, okay? And then we're also going to describe the formation of the optical image by mirror, image formed by a plane mirror. We're going to look at how the image is being formed by a plane mirror, and we're going to give the characteristics of the image formed by a plane mirror. They are laterally inverted, they are upright, they are virtual. We're going to talk about all of that. Now, we're also going to state that for reflection, the angle of incidence is equal to the angle of reflection. The angle of incidence is equal to the angle of reflection. We're going to recall and use the relationship for this simple case. And then we're also going to use simple constructions. We're going to use simple construction, measurements, calculations, okay, for reflection by a plane mirror. Now, the first objective, what we're going to learn, is the law of reflection. Reflection simply means the rebounding of light when it reaches a surface. When light reaches a surface, when light touches the surface, it rebounds. That's called reflection, rebound. Light is coming like this to a surface, it hits the surface, then it's rebounded. So that's and this is our normal. This is the normal, okay? So this is the incident angle, angle I, and this is the reflected angle. So the rebounding of light when it touches a surface is called the reflection. It's called reflection. Now let's take a look at, for example, how we have a lamp in the room, and we have the light will shine, send rays to this image on the wall. You see the image you paste on the wall? How do you see it? The reason that makes you see it, okay? Ordinarily, if there's no light, if you go to a dark room, will you be able to see this image on the wall? No, you'll not be able to see the image of the wall. So the point is that the light ray, they are incident on this image on the wall. Then the image of the wall will reflect the light. You see it's a smooth surface. Will reflect the light to your eyes. That's how you're able to see the image on the wall. If you want to see a simple experiment, you can switch off the light in the room in the dark. You see, you'll not be able to see anything. You'll not be able to see anything. So the real reason why we're able to see this object is this image or the object on the wall. This object on the wall that you paste on the wall, this animal on the wall, is a non-luminous object. By non-luminous, we mean that the object does not produce its own light. Do not produce and transmit its own light. The object that produce their own light, like the sun, they produce their own light. The lamp can produce its own light. Okay, they are luminous. Those objects that can produce their own light, they are called luminous objects. Objects that can produce their own light, they are called what? Luminous objects. Like lamp, like sun, anything that can make its own light, okay, they are called luminous objects. But the ones that, like the moon do not make its own light. The moon reflects the light that it gets from the sun to the earth. Okay, like this object on the wall is not producing its own light, but it can reflect the light that comes to your eyes. Then you're able to see. So you can see this ray is reflected ray, and why this ray is incident ray. This ray, the light from the lamp, is incident to this place, and then this is a non-luminous object, cannot produce light, but it can reflect light, and that's how the light comes to our eyes. Now let's move on quickly. Now let's define this following from based on what we have talked about just now. The lamp, the image, the object on the wall, and how it's reflected to our eyes. First of all, we say reflection is the rebounding of light at surface. Yeah, I think we already explained this. It's the rebounding of light when it hits a surface. When a light hits a surface, it rebounds. The rebounding of light when it hits a surface is called reflection. Now, what is incident ray? Incident ray is the light ray that hits the reflected surface. The light ray that hits the reflected surface. Like, for example, this is the light ray that is traveling to this whatever you placed on the wall. So this is an incident ray. It's the light ray that hits the surface. That's called the incident ray. Then the reflected ray is the one that is being reflected, that is being rebounded. Okay? Okay. Now, point of incidence is the point at which the light ray hits the reflected surface. The exact point where the light ray hits, this is called the point of incidence. Okay? This is called the point of incidence. The point where the light hits the reflected surface. For example, if we draw it here, where is the point of incidence? If this is your normal line, and this is your incident ray, this is your incident ray. Okay, this is the point of incidence because this is where it touches the surface. This is where it touches the surface. Could be a plane mirror. This could be a mirror, and then this is the reflected ray. Okay, this is the reflected there. Let's assume this one angle of incidence, angle I. Angle of incidence is called angle I, and angle of reflection is called angle R. These two angles are equal. Okay, they are equal. This is the incident ray. This is a ray. This one is called the line is called the ray. Incident ray R. Okay, and the reflected ray. This is the reflected ray. Okay. Now, what's the reflected ray? A reflected ray is a light ray that rebounces off the reflected surface. The one that rebounced off the reflected surface. This is the reflected surface. This one. Okay. This is the surface. This is the surface. The light that rebounds off the reflected surface is called the reflected ray. It's called the reflected ray. Okay. The light that rebounds off the reflected surface is called the reflected ray. While the one to the light ray that hits the reflected surface, this is the reflected surface. You can call it reflected surface. Okay. The light ray that hits the reflected surface is called the incident ray. The light ray that hits the reflected surface is called the incident ray. The light ray that rebounces off the reflected surface is called the reflected ray. Okay, so these are, that's point, about 4 of them we need to know. What is the reflection, what is incident ray, what's point of incidence, the point at which the incident ray hits the reflected surface. The point at which the incident ray hits the reflected surface is called the point of incidence. So we need to know all this definition. Now let's take a look at a simple example. This is practical. This type of question you see in paper 6. They will ask you to show design and experiment to investigate the law of reflection. An investigation to investigate the law of reflection. Okay, so what do? You're going to need a surface on a plain white paper, a mirror on a plain white paper, and you're going to take a ray box and you shine light from this ray box to this surface, and you see how the light is being reflected. So we're going to draw the normal and we measure the angle. We use a protractor to measure the angle of incidence and measure the angle of reflection. And then we see at this point, we see the values are same because the law says that the angle of incidence I equals the angle of reflection. That's the law of reflection. The law of reflection says I equals to R. The angle of incidence equals to the angle of reflection. The angle of incidence is equal to the angle of reflection. Now, what is the normal? We've mentioned the normal, right? We've said the reflected surface, in this case, is the mirror. What is the normal? The normal is an imaginary line. That's why we use broken lines. It's an imaginary line that is perpendicular, that's 90 degrees to the reflected surface. Imaginary line that is perpendicular to the reflected surface at the point of incidence. This is the point of incidence. At the point of incidence. Is that okay? The angle of incidence is the angle between the incident ray and the normal. Many people, they make mistake. Cambridge, they want to catch you, they put the value here. You can put 50 here, and then they ask you what is I and what is R. If they put, for example, if you put an angle here, we say 50 degree. Many students, they always make the mistake. Oh, they say, oh, okay, and incident ray is 50. No, incident ray is not 50. The incident ray is the angle between the incident ray is the angle between the incident ray and the normal. You must always look at the angle between the incident and the normal. The reflected is the angle between the reflected ray and the normal. So if you first of all calculate this value, the reflected angle. So you calculate, because this is perpendicular. Since it's perpendicular, you say 90 minus 50. To get an arrow, you say 90 minus 50. That you get 40, right? You get 40. 90 minus 50. So R equals to 90 minus 50, which is 40. So once we get 40 for R, remember the incident angle will also be 40 because they are equal. So if here is 40, if here is 40, here is also 40. Here is also 40. Is that okay? Here is also 40. So in multiple choice, Cambridge paper 2, Cambridge Igcse, you're always being asked. They can fool you and put the value here. They want you to tell the angle of incidence or an angle of reflection. Now let's move on to the next one quickly. The normal we already defined. We say the normal is the imaginary line that is perpendicular to the reflected surface at the point of incidence. So you need to know all this definition. The normal is an imaginary line that is perpendicular to the reflecting surface at the point of incidence. The angle of incident I is the angle between the incident ray and the normal. The angle between the incident ray and the normal, this one. The angle between the incident ray and the normal. This is the normal, this is the incident ray, this one. So this angle is called angle I. It's called angle I. Okay, so we need to, and the same goes with the reflected angle of reflection. Angle of reflection is the angle between the reflected ray and the normal. Is that okay? Now, just look at exactly what I was telling you just now. For Cambridge, they can ask you to compute the value of I and R. Compute the value of I and R and state the law of reflection. State the relationship between the angles of incident and the angle of reflection. Okay, so what you need to know is that this is not angle I. Many students will just say, oh, 50. It's not 50. Okay, remember this is angle 90. The whole of this is 90 degrees. You can see here is 90 because it's perpendicular. Any perpendicular, horizontal and vertical is 90 degrees. So this is 90. The whole of this place is also 90. Since it's 90, you say 90 minus 50, you get 40. And remember the incident angle, since it's coming to the point of incidence, this ray is traveling to the point of incidence, so here is the incident ray, this incident angle. So this incident angle is 90 minus 50, which is 40. And if incident angle or angle of incidence is 40 degrees, then the reflected angle will also be 40 degrees. So this is the, first you draw this and show the reflection. This is angle I, this is angle R, and then you do the calculation. What is the angle of incidence, what is the angle of, we did the calculation, and then we get 40. Is that okay? Now, another thing that we can do is to investigate the characteristics of image formed in a plane mirror. The characteristics of image formed in a plane mirror. So you can put an object one side, put a mirror, you put a board, a woody holder. This is a woody holder. This is a soft board. This whole is a soft board, and this is a graph paper. You put a graph paper on top of it, on top of the board. Then you put an object. You put a mirror here. Put an object so you can see the distance from the object to the mirror, and it will be showing on the mirror the same distance away from the object. Okay, so now the characteristics of image in a plane mirror. This we need to know. First of all, image formed in a plane mirror, they have the same size as the object. Image have same size as the object. That's the first thing you need to know. The image is the same size as the object. If this one is like this, if the object is like this, the image will also be like this. The image will also be like this, away from the mirror. It will also be same size as the object, away from the mirror. Okay, it will also be almost same size as the object, away from the, let's say here is the mirror. Here is the mirror. Okay, the distance from the object to the mirror is the same distance from the mirror of the object away from the mirror. The same distance of the image away from the mirror. The same distance. So object distance and image distance, they are same in the case of a plane mirror. Okay, so one of the characteristics is that we say they have the same size. The object, if this is the object and this is image, the size are same. The size of the object and the size of the image, they are same. They are same. That's number one. Number two is that they are laterally inverted. What do you mean by laterally inverted? Okay, when you are facing the mirror, the image will be facing you also. If you take a mirror and look at yourself in the mirror, you are looking at the mirror. The image is also looking at you. They are laterally inverted. If you take your two palms, if you look at them, they are looking at each other. They are laterally inverted. They are not looking opposite like this. So this is what we mean by lateral inversion. Okay, for example, if this is letter E, this is what we mean by laterally inverted. This is the mirror. The image will be like this. Will be like this. They used to ask this in multiple choice, how the image will look like. The image will be like this. We'll also be looking back at the mirror. Not like this, not like this, not E the way it was originally. Not E like this, not the way it was like this. No, it will be facing back the mirror, okay? So this is meaning of lateral inversion. So the image in a plane mirror, they are laterally inverted. They are upright. So if the object is standing up, the image will also stand up. Okay, not turned upside down. They are upright. So this is the third characteristics. Okay, they are virtual, meaning they are not real. They are not. The mirror is not a screen. Images are not formed on the screen. They are virtual. Because if you take a mirror and you look at yourself, Are you actually behind the mirror? No, you're not behind the mirror. So it's virtual, it's not real. Okay? Then same distance. I already explained the distance. The image distance, the object distance is same as image distance. U and V, they are equal. Okay, same distance from the mirror and away from the mirror. The distance is same. So there are about 5 characteristics of an object formed in a plane mirror. Now let's take a look at this. What do you mean by laterally inverted? Okay, you see the word physics. There are several letters. Physics is even a several letter. There are several letters in the word physics. See, physics is a several letter. 1, 2, 3, 4, 5, 6, 7. No wonder. Physics is a several letter. You know, several letter words are powerful words. Okay, I'm just joking. Okay, so now how will it be on the mirror? How will it be on the mirror? So that's the question. You go to as puzzle. You go to solve. Remember, they are laterally inverted. So physics, how will it be? It will not be physics like this. It will be like this, right? It will be like this. Okay? H is the same as H. Okay? So you're going to solve this, complete the answer. Complete the answer. Okay, it will start from this way. Remember, physics is far end. This one will also be far end. Sorry. P will be on this way. P will be on this way. P will be on this way. H is same, right? Because the lateral same, both the lateral inversion is same. H is this way. Y is same, right? Y is same. S is laterally inverted like this. Not the normal S. I is same. I will be same. C will be like this, right? Laterally inverted. And then S will also be like this. So physics. So this is the physics. This is the image of the physics. This is the image of the physics. Okay, this is what you have here. This is what you have. Physics. Okay, that's what you have. Okay, they can ask you how many of them are laterally inverted. P is laterally inverted. H is same, right? H is same. Y is same. S is laterally inverted. This is the second one. I is same. This is the fourth one, laterally, and this is also laterally inverted. Okay, so that's that. Let's move on. The ones that are same are 3. Yes, the ones that are laterally inverted are 4. Is that okay? I think these were part of the questions. They say, hold the word up. There are several letters in physics. Hold the word up in front of a plane mirror as shown in figure 12.8. Write down how these letters appear in the mirror. How many of these letters appear to be different when the word is reflected? How many are different? 4 of them. Write down the letters that appears to be same. 3 of them. You write those letters down. So these are the answers to that question. Now let's move on. Let's take a look at this second learning objective. Drawing the ray diagram for plane mirror, point object and extended object. So how to draw the plane mirror? That's another learning objective here. Now you have an object here. Here's a mirror. Okay, here's a mirror. How is the image formed? So you know the object will reflect light to this place, right? Light incident here will be reflected, right? It will be reflected towards your eyes like this. It will be reflected to your eyes like this. It will be reflected to your eyes. Okay? It will be reflected to your eyes. Where will the image be? Behind the mirror. We show this with broken line. Extend this to with broken line. Sorry, broken line. Same distance away. Also extend this one with broken line. With broken line. Okay. So you can see this is the image I behind the mirror. Behind the mirror. Whereas this is the object O in front of the mirror. So this is how the image is formed in a mirror. Now let's take a look at some of the drawing a ray diagram from a point object. Okay. Let's say object is here. You draw the ray to this place, right? You draw two rays to this place. Okay, they will be reflected to the eyes, and then they will be laterally formed behind the mirror with broken lines. Okay, see, this is the second point. Object. So if you have object here, image will definitely be same distance away from that place. Okay, that's the first thing you note. Then you draw ray to the mirror, two ray from here, starting both of them starting from this point to the mirror, like we had here. One, two, at least two ray. Where they meet, reflected to the eyes. When they hit the mirror, they are reflected to the eye. But these rays are traced with broken line to meet this point where the image appears to be. So this is how to draw a ray diagram. In physics, they ask this in the exam. They'll give you an object, they'll give the eyes here, they can ask you to draw the ray. They ask you to draw the ray, okay? It's possible. Or they draw for you, they ask you certain question they want to ask you. Like, for example, they can ask you to show where the image will be. This is the object. So you draw two rays, both of them will start from here, not and separate. They will start from here, separate, and then reflected to the eyes. Then you use broken lines to join both of them to meet at this point. Is that okay? And they always note that the image distance equals to the object distance, and so on and so forth. So I think this one we are clear. This is it. We've showed it here. We started to show it. But you have to draw the ray here, the incident ray. This is the reflected ray. And this is what is the virtual one that is formed behind the mirror. Okay, see, look at the incident ray to the mirror, and then reflected ray to the eyes, and then this broken line shows the virtual one, that how the image is being formed behind the mirror. Now let's move on quickly. There are many more. Okay, they give you object. You see object like this. How will the image be? The image, remember, is a virtual image, so we're going to use broken line. So you're going to draw a ray from a ray of light, right? From this point, a ray of light to this place, two rays of light to this place, and then reflected to our eyes. Reflected to our eyes, and also two rays here. The one here will be literally drawn to this place. The one from here will be taken to this place. Okay, and then you'll be able to draw the image with a broken line. Exactly this way, same height, same length, and so on and so forth, and it will be laterally inverted. See, this one is going this way, while this one is going this way. So we should be able to draw image in a plane mirror. So these are also objective learning practice questions for you. They give you an object here. The image will definitely be somewhere here. The eyes is here. So you draw it to here and you bring the broken line steadily to reach the image somewhere. Now they give you something here. See, something to try. The eyes here. You draw a ray of light from here to this place. Two rays. Extend to the eyes. You draw two here. Okay, extend to the line. Both of them you extend then to this place, and you'll be able to get a broken one of the image here. You'll be able to get a broken one of the image here. Okay, you'll be able to. Okay, so just like we have learned, use that opportunity to draw that. Okay, now let's go to refraction of light. Refraction. Refraction is the second part of this topic, light. We finished reflection. Now we go to refraction. Refraction is the body of light. The body of light when it hits a boundary. The bending, not rebouncing. The light will bound, it will go through it and bend. Reflection was the rebound, the light will rebounce. Refraction, the light will bend, but will still go through the medium. To pass through it, to go through it, but you bend, change direction. Okay, so these are the things and we're going to learn refractive index. Okay, so let's see the first learning objective. The first one is to investigate the law of refraction. Now, in the law of refraction, it's called Snell's law. Law of refraction is called the Snell's law, which is equal to the refractive index. This is the symbol for refractive index. Is sine I over sine R. Sine of incident angle. The sine of remember in this case, the incident angle or angle of incidence is not equal. It's not same as the refracted. Okay. Here, for me to differentiate reflection or refraction and reflection, I'll use arrow prime. You know, before we use arrow for reflection. Now for refraction, let's use arrow prime. Okay, so the refractive index is the, or what we call the Snell's law, is the sine of the incident angle over the sine of the refracted angle. Is that okay? So you find both angles, you do their sine, and then you do their ratio or fractional, and then you get the refractive index, which is called the Snell's law. It's a constant. Okay, it's a constant, which is called the Snell's law. Okay, so now let's take a look at objective 2 to investigate the law of refraction. So the law of refraction is called the Snell's law. In this case, we're going to be dealing with two media, maybe air. Let's say this is a glass, piece of glass. Okay, and this is the normal. This is the normal at this point, and maybe there's a normal also somewhere else here. Okay, this air, this air, this air. This is glass or water, whatever you want to call it glass. But what we know is that it's a different medium. This glass, and then this air again. Like when it comes out, it goes to air again. A ray of light that is coming from here, let's change our listing. A ray of light coming that is coming from here, that is incident. The difference between refraction and reflection. You know, if it's reflection, it would have gone this way. This one will bend because it's coming from optically less dense medium to optically denser medium to bend towards the normal. Okay, this is where we should have put our this thing. So it will bend towards the normal. So this angle is called angle of refraction. This one, arrow prime. It's called the angle of refraction, arrow prime. Why this angle? This angle between the incident ray and the normal, this normal, okay, the incident ray and the normal, the angle is called angle of incidence, angle I. So whatever value here is, let's say 30 degrees, so you say sine 30, you say refractive index is equals to, sine 30, which is called Snell's law, over, let's say the refracted ray is 80 degrees. Let's say 80 over sine 80 over sine. So you press your calculator, you get the value of the over sine 80. You get, when you do this, you get sine 30 divided by sine 18, you get the refractive index. And that ratio is a constant, which is for every medium between glass and air, that's you get 1.6, right? This one will give you, so it means the refractive index in this case is 1.6. It means the refractive index is 1.6. Okay. Now, what is refraction? Now we're looking at it. We've said is the bending of light as it passes from an from one optical medium to another optical medium. So when light is changing, let's say from air to glass, or air to water, or water to glass, or water to air, whenever the ray of light is changing medium, from vacuum to water to whatever, it's changing a medium, it will bend. Either it bends towards the normal or it will bend away from the normal. Okay. In scenario 2, where it will bend away from the normal, let me show you that. Because the one I just showed was the one where it bends towards the normal. So because if you're coming from optically less dense medium, air is less dense than glass. In light, we use the word optical. We use that terminology, optical. Okay. Air is an optically less dense medium compared to glass. So when light is coming from an optically less dense medium to an optically denser medium, it will bend towards the normal. You see this ray will bend towards the normal. But if it's now going out, let's say this is another normal, this is another normal. If it's now going out from glass to air again, it will bend away from the normal. Why? It's coming from a denser medium to a less dense medium. So it will bend away from the normal. The light will bend away from the normal. See, this angle is bigger, right? It's bigger than this small angle here. It's bigger than this small angle here. It's bigger. This one is bigger. It will bend away from the normal. So when light is traveling from an optically denser medium to optically less dense medium, it will bend away from the normal. This angle, this refracted ray will be larger. If it's coming from glass to air, meaning glass is an optically denser medium, to air, which is an optically less dense medium, to bend away from the normal. But if it's coming from air into a glass, it will bend towards the normal. Now, what if the ray of light is entry through the normal? What will happen to the ray of light? Let's say this is our normal. The ray of light is not coming at an angle. It's not coming like this. It's coming straight from the top. It's coming straight from the top. Let's take a look. It's coming straight from the top. It's coming straight from here through the normal. What will happen to it? It will not be deviated, continue like that. Any ray of light coming through the normal will be undeviated. We use the word undeviated. It is not deviated. It will continue its journey like that. Any ray of light coming through this will be undeviated. It will continue its journey like that. So we know what is refraction now. Refraction is the bending of light. So when light is traveling from air, when it gets to this point of incidence, the boundary of this glass, it will refract. It will go through the glass, but it will refract. It will bend towards the normal. That's called that bending, or that bending of the light ray instead of continuing straight. You know, its journey is supposed to be straight like this. As it's coming like this, look at it. As it's coming like this, it's supposed to go straight, right? It's supposed to go straight. But it does it. It does it. It bends towards the normal. That bending of the light as it changes medium is called refraction. It's called refraction. The bending of light as it changes from one medium to another medium is called refraction. Now, angle of refraction is the angle between the refracted ray and the normal. We already know this one. Okay, so you can see experiment you can do, like I already said. If a light is traveling straight away into this from the normal, is undeviated. It will not bend. It will not bend. When you shine a bulb through the top like this, straight away to it, it will not bend. But when you shine it at an angle, not straight away from a normal. Anytime you do it from straight away from a normal, from the top straight line like this, it will be undeviated. It will not bend. But when you shine it at an angle, of incidence, the ray is coming from air, because air is less dense, optically less dense, so it will bend towards the normal. This angle R will be smaller than this angle I. It will bend towards the normal. On emergent, when it's emerging from here again, this is called emergent ray now. When it's exiting the glass, it's called emergent ray. And this angle is called emergent angle. Okay, remember the first angle is angle of incidence. Okay, and the first ray is called incident ray. Then when it bends towards the normal, this is called refracted ray, and the angle is called refracted angle. And then when it's exiting the glass, it's called emergent ray, and the angle between this emergent ray and the normal is called the emergent angle. Is that okay? Okay. So I've explained those one. Let's move. This is the experiment trying to show you. You have two ray box, one through the normal, we show or deviated ray as it comes out, and the emergent ray. You have the other one that forms all the angle because it's at a certain angle, and you get the incident angle, refracted angle, and the emergent angle and emergent ray. Okay, so you'll be able to, paper 6, you'll be able to explain this experiment in paper 6 in case you're being asked. Now, how is refractive index and the speed of light related? We've already taken a look at the formula. You say refractive index, you can write it in so many ways. And the speed of light, you say, first of all, remember the first one we talked about was that refractive index was sine I over sine R, which is Snell's law. They ask you to state Snell's law, you don't know how to state it, just write refractive index N equal to sine I over sine R. R in this case is angle of refraction, not angle of reflection. Angle of refraction. So sine I over sine R over sine R. Okay, this is one way of stating the relationship between a refractive index. This N, this thing that looks like N, is called the refractive index. It's called what? The refractive index. This one is called the refractive index. That's one way. Another way of stating it, because they say how is it related to speed of light? Refractive index is the speed of light in air. So let's permit us to use V for speed, VA as the speed of light in air or vacuum. You can use air or vacuum over speed of light in a medium. Any medium, could be glass, could be water, so any other medium. So refractive index can be calculated, or you can be given refractive index and you don't need to be given speed of light. They assume you know it 3 times 10 to the power of 8. So they will just ask you to calculate the speed of light. If they give you the refractive index, you are expected to calculate the speed of light in the medium. You make this one the subject of formula. Okay, so this is the equation for that. Okay, now let's see, since we've written the equation, let's see how for diamond, refractive index, what's the refractive index of diamond? Because you make this one, you say the speed of light in air divided by the speed of light in the diamond. So they'll give you the value of diamond, the speed of light in diamond, 1.25 times 10 to the power of 8, 1.25. So you say 3. So if you want to calculate the refractive index of diamond, you say the speed of light in air, which is 3 times 10 to the power of 8, divided by the speed of light in diamond, which is 1.25 times 10 to the power of whatever is here, 8, right? I think this is 8, times 10 to the power of 8. So when you do this, you get the refractive index. You get this refractive index, how they got the refractive index. So the same here, this is 2 times 10 to the power of 8. So you say 3 times 10 to the power of 8 divided by 2 times 10 to the power of 8, you get 1.5. Because 10 to the power of 8 will simply cancel 10 to the power of 8. Okay? So this one will now be 3 divided by 2. 3 divided by 2, you get 1.5. That's how we got the refractive index in glass to be 1.5. So different material, we can calculate their refractive index. This table is showing that. Now let's move on quickly. What are the daily phenomenal applications of refraction? Okay, one of the things that where you should be careful is that it does not show the real depth of object when they're placed in water. So sometimes you go to a swimming pool, you see the pool looks as if it's very shallow. You can literally see the bottom. It looks as if the depth is very shallow. So because that's not the real depth, that's called apparent depth. Apparent depth. Okay, that's the apparent depth. It's not showing you the real depth. The real depth is far below. Okay, so there'll be when you can see the bottom of rivers or lakes or swimming pool, don't jump into them if you don't know how to swim, because that what you're seeing is not the real depth. So that's one application of refractive index. Okay, it shows you an apparent depth, not the real depth. The real depth of the object is way below, down below, but it's showing you as if the object gets to this point only. Showing you as if the object gets to this point. So that's one application of refractive index. Now let's move on to point 30.3, total internal reflection and critical angles. Okay, total internal reflection and critical angle. Now the learning objective here is the total internal reflection. The objective is to investigate the critical angle in a total internal reflection. Okay, now to do this, we must take an optically denser medium. We must take an optically denser medium. Anytime you make a ray to pass through normal, the ray will be undeviated. You go like this. There's no angle form, nothing. It will not be refracted, it just goes through. It's undeviated. But if you increase the ray, then you move the ray box to this point, you shine it, you get reflected ray to be reflected. You increase it again, maybe like around 41. You shine the ray from here. You increase again. Let's say you make the angle of incidence for around 41 or 42. At that angle, where the reflected ray, most of it will be passing through be refracted here through the boundary. Please pay attention. This is the most important part of this lesson. See, the point where, but you must do this from optically dense medium to a less dense medium, not from air to glass, maybe from glass to air, or from glass. That's one condition of this experiment. Okay, when an optically denser medium, when a ray of light is traveling from an optically denser medium to a less dense medium, the angle of incidence for which the refracted ray is at 90 degrees with the normal. It's at 90 degrees with the normal. This is 90 degrees. Or it's moving at the boundary between the two media. It's moving at the boundary. This is the boundary between the air media and glass medium or water medium. Okay, this is the boundary. The refracted ray, instead of being refracted this way, either towards the normal or away from the normal, instead of being, okay, it will be away from the normal because it's coming from a denser medium. Okay, instead of following here, but it will be refracted to pass through the boundary. It's neither out nor in. It's not even reflected back in the medium. It's just moving at the boundary. The angle, whatever angle of incidence that create that scenario, that make this scenario to happen, that angle is called critical angle. the angle is called critical angle. Okay, if they ask you what is critical angle, you say critical angle is the angle of incidence. First of all, when a ray is traveling from an optically denser medium to optically less dense medium, when a ray of light, that's how you start. When a ray of light is traveling from an optically denser medium to an optically less dense medium, the angle of incidence, this angle of incidence, for which this one happens, the angle that created, that enabled this to happen, the angle of incidence for which the refracted ray is moving at the boundary between the two media or is refracted at 90 degrees is called, that angle of incidence is called critical angle. It is the incident angle that we call the critical angle. Take note. The angle of incidence for which the refracted angle or refracted ray is moving at the boundary between the two media is called, that angle of incidence is called the critical angle. Okay? And it doesn't just happen, it's a certain value. Let's say between 40 to 42. Okay? You increase your ray angle from maybe from 10 to 20. What do you get? Everything will be, most of the thing will be, will be refracted. Will be refracted out here. Most of the ray will be refracted. You increase it to 30, still most of the ray will be refracted out to the air. Then you get to a certain angle, let's say 40 or 41 or 42. Then you see most of the ray will not be refracted out, neither reflected in. It will be refracted to be passing through the boundary or at 90 degrees to the normal. So when the ray, most of the ray is refracted to be passing through the boundary between the two media or 90 degrees to the normal, the angle of incidence that creates that scenario, that phenomenon, that angle of incidence is called the critical angle. You must be able to define this in physics exam. You must be able to illustrate it in physics exam. You must be able to demonstrate it in physics exam. And again, total internal reflection is, when I increase this value from 40, let's say 63, I increase the value of the incident ray now. Let's do this with a different coloration. Let's say we increase the value of the incident ray to 63 or 60 something. This angle is now bigger than the critical angle. When you do that, all the ray will be totally internally reflected. This is what we call total internal reflection. All the ray, no one will be refracted out, no one will be refracted to pass through the boundary. All of them will be reflected back in the same medium. Okay, that one is called total internal reflection. That's what we call total internal reflection. So we start from, first, you choose angles with this ray box. You choose angles maybe 10, 20, 30, up to 40. You get reflection out from here. You get reflection out. Then when you get to a certain angle, let's say 40 or 42, between 40 and 42, the angle of incidence for which this one will be moving at the boundary is called the critical angle. When you increase it to 60, 61, 62, 63, then all the rays are reflected. That point is called total internal reflection. Okay, so here we are at the beginning. Okay, at the beginning we have most of the ray refracted. You can see, refracted away. Only few are reflected. That's why we call it weak reflection. Only few tiny ones are reflected back in the same medium, but most of the ray are refracted because the angle here, angle of incidence, is small. The angle of incidence is small. Okay, but remember, it must be an optically denser medium to optically less dense medium. Like glass, we are doing from glass to air. We are doing from glass to air. This medium is air. Out here is air. Out here is air. Is that okay? Out here is air and here is glass. So you must choose from a denser medium before you talk about critical angle or total internal reflection. You must start from a denser medium. So you are shining the light through this glass, and then most of the rays are refracted out, and only few are reflected inward. So here we don't have a critical angle yet, and we don't have total internal reflection. Now, when do we have a critical angle? It is when you increase this angle of incidence from 30 to like 40 or 41, 42. Then you see that most of the ray will now be reflected at 90 degrees to the normal. 90 degrees. They will be refracted at 90 degrees to the normal. So the angle of incidence, for which most of the ray are refracted 90 degrees to the normal or are moving at the boundary between the two media, That angle of incidence is called the critical angle. So they ask what is critical angle when a ray is traveling from an optically denser medium to a less dense medium. The angle of incidence, you start with the angle of incidence for which the refracted ray is at 90 degrees to the normal. Here is the normal. It's at 90 degrees to the normal. This broken line is the normal. It's at 90 degrees. See, this is the 90 degree. This angle is at 90 degrees. This one is at 90 degrees to the normal. Or you can say, use the word moving at the boundary between the two media. That angle of incidence for which this happens is called the critical angle. Okay, only weak ones are reflected. Still, only weak ones are reflected in. Now, the third scenario is the total internal. You increase it even beyond angle 43, maybe 42. You increase now you can see the angle of incidence is greater than the critical angle. You can see meaning you increase the angle of incidence to like 60 or 50 something or 60. It's greater than the critical angle. When it's greater than the critical angle, all the ray will be reflected back in the medium. No one will be refracted. All of them will be. So this point where all the rays are reflected back in the same medium is called total internal reflection. So if you want to define total internal reflection, this is when a ray of light is traveling from an optically denser medium to an optically less dense medium, and the angle of incidence for which all the rays are reflected back in the same medium is called total internal reflection. It's called total internal reflection. Okay, we hope you get this scope. The definitions are here for critical angle and for total internal reflection. You pause the video and look at the definition. I've already explained the definition. These are the scenarios, all four scenarios, where the ray is passing through the normal, no one will be deviated, or we just go straight like this, no one will be deviated. When you have a small angle of incidence, most of the ray will be refracted out from here. Only weak few ones will be reflected back in the medium. When you increase it to a level to like around 40, most of the ray will be refracted to move at the boundary between the two media or at 90 degrees to the normal, while few ones are reflected. The angle of incidence is called critical angle. When the angle of incidence is now greater than the critical angle, let's say you increase the angle of incidence to around 60 or 63, then all the ray will be reflected back in the medium. That is called total internal reflection. So pause the video, look at their definition. Okay, the definitions are here. I've explained the definition, and these are the critical scenario with it. Now let's take a look at the application of total internal reflection. Where do we apply total internal reflection? You know the optical fiber is used in telecommunication, optical fibers in telecommunication industry and in medical industries. Okay, and how? Total internal reflection, the ray enters through here, it hits the boundary of this fiber, then they are totally internally reflected down here. It hits here again, all of them will be totally internally reflected in. This is how red light travels in an optical fiber. It hits this boundary again, they are all totally internally reflected. So this is how light, you should be able to draw this in the exam. This is how light travels in the optical fiber. Okay, one application of total internal reflection is in telecommunication, used as optical fiber in telecommunication and medical industry. Another application of it is used in periscope. Okay, you are here, you can see object that is hidden here, because when light hits, there's a 90 degree right angle that is mirror that is placed here, and also right angle that is placed here. So when the object is here, the ray travel hits here. When it hits here, totally internally reflected here. Then it hits here again, they are totally internally reflected to your eyes. This is how you that is here is able to see something that is here. Normally, you are not able to see it because there's a big blockade. There's a big blockade that enables. So with a periscope design like this, you'll be able to see objects in a very hidden location, because the light are able to be transmitted. When they hit this boundary, this one, they are totally internally reflected down. They hit this second hypothesis boundary again, then they are totally reflected to your eyes. Then they are also in use in binoculars. Okay. So these are areas where we use in binoculars, in periscope, in optical fibers. These are areas where you use total internal reflection, the application of total internal reflection. So stop here, pause, and answer this question. Okay, answer this question. Explain what is meant by critical angle. Clearly, draw clearly a diagram, a label diagram to show total internal reflection. Okay, which has been seen. State 2 application of total internal reflection. These are exam questions you will find in this area of physics. Now let's move to the refraction by thin lens. I think lens will be the last section of this video. Okay. Now, lens, what determines the paths of light through a lens? Okay. First, we have two types of lens. We have the converging lens and the diverging lens. Converging lens is a convex lens, while the diverging lens is a concave lens. Okay, this is a convex lens. Now, it's able to diverge, causes light rays to converge at a point. Because it has one rule, any light that is parallel to the principal axis, this is the principal axis. This is the optical center of the lens. Any light that we draw a straight line, a horizontal straight line at the center of the lens, that one is called the principal axis. Any line that is parallel to the principal axis is refracted to pass through the optical point. It's refracted. You know, when you get here, it will be refracted. It will be refracted to pass through the optical point. If including this one, this ray, when it gets here, it's refracted to pass through the optical point. Even this one will be all deviated because this one is the center. Will be all deviated. This one that is parallel to the principal will be refracted. The one below now will be refracted to still come and pass through the focal point. Also, this one will be refracted when it hits this point on the lens. It will be refracted to pass through the optical point. So it converges the rays at a point to meet at a point. That's why it's called a converging lens. So a convex lens is a converging lens, while a concave lens is a diverging lens. In the case of concave, this is a convex lens. Okay, we use this. We're going to study this one the most, the converging lens or the convex lens. While this concave lens is a diverging lens. It's not a converging, it's a diverging. Any ray that is coming here, okay, it will be broke. The virtual one will be formed here. The real one will be refracted away. We diverge it away. The real one will be diverged away, diverged away, diverged. All of them will be formed virtually to meet here. To meet here, virtually to meet here. Is that okay? Now, how do we use a lens to form an image in a How do we use lens to form an image in a diagram? Let's quickly show like 2 or 3 scenarios. Let's quickly look at these two and the use of this one in long sight. And we use converging lens for long sight, and we use diverging lens for short sight. We use diverging lens for short sight, we use converging lens for long sight. Okay, before we do that, let's take a look at the image that is formed. If I have a lens quickly, time will not is getting longer. Let's quickly to draw an image in a lens. First of all, this is the principal focus. And sorry, this is the principal axis. Okay, this is the center of the lens. This is the center of the lens. Okay, you choose 2 points, you call them the focal point. Choose these 2 points, you call them the same distance to the center of the lens and same distance away. You call these 2 points focal point. Okay. Now, we need to know 3 rays that will enable us to draw an image in a lens. First is that when a ray of light is parallel to the principal axis, a ray of light that is parallel to the principal, this is the principal axis, this one, this long horizontal. A ray of light that is parallel to the principal axis will what? Will be refracted to pass through the focal point. Let's say here is your focal point. Here, this point. Let's say here is your focal point or principal focus. Either you call it focal point or you call it principal focus. Okay, will be refracted to pass through the focal point. That's number 1 ray diagram, ray that enables us to draw an image. The second one, any ray that is passing through the optical center, let's say this is the principal axis. Okay, any ray that is passing through the optical center, like this, will remain deviated. You know, right? Will remain deviated. This is remain deviated, will not be refracted. That's the second rule. The third one is, what of a ray that is coming from the principal focus? Let's say a ray, the third rule, what of a ray that is coming from the principal focus? Let's say this is the principal axis. This is the axis, principal axis. This is a principal focus. This is the principal focus. Let's assume these are the principal focus or focal point F. Okay. Any ray that is coming like this, what if the ray is coming from here? Is coming from the focal point or principal focus, and it hits the lens. The ray is coming like this, and it hits the lens. We have a video on lens, okay? If you want more on the lens, Waidsum Academy already have a video on lens, okay? And how to draw the image in the lens. So this one will be refracted away like this. If it's coming from the lens, if you look at this, it's just opposite of the first rule. This is just opposite. This is just opposite of the first rule, right? Because the first one says, if it's coming parallel to the axis, it will be refracted to pass through the focal point. And the last one says, what if it's now coming from the focal point? It hits here, it will be refracted parallel to the axis. That's the last one. They are same thing. Okay? This one says any ray that is coming through the optical center will be undeviated. We just need two of these to form an image. We need at least two of these to form an image. Okay, so if you want to know this aspect, please watch our video on how the ray is drawn. Okay, or let's show only one. We have, let's say, one lens. We have a lens here. We have the principal axis. We have the principal axis. This is a focal point. This is another focal point. Okay, let's say here is an object, a candle, light. Let's say here is an object. This object will produce ray that will move through this space, right? We always use arrow to show the direction of the ray. Okay, you must draw the center line, because that's where refraction takes place. So it will be bent, it will be refracted to pass through this optical center, this one. Then anyone coming from the optical center will be undeviated till they meet. Okay, will be undeviated till they meet. Where they meet, that's where the image is formed. You draw. So that's why we say this one they are inverted. The image in this one are inverted. The candle will be inverted. This is the image. They are real, so you don't use broken line. The image formed by a lens, they are real. By convex lens, they are real image. This is the image formed. To be inverted, okay? And then you can now describe this characteristic. But we have a video on this one. Please check our video on lens in Waidsum Academy. Thank you for joining us.